Here's an example of redox stoichiometry. Like all other stoichiometry, you first have to come up with a reaction and balance it. Then you go on to determine your knowns and your unknowns, and then the math starts. Find the moles of your known, find the moles of your unknown, then you solve. So, with redox, the only difference is that you get to use your predicting redox reactions rules in order to get your balanced reaction. So you get to use your data table, which is pretty nice. So the question will come in the form something like this, perhaps, where you're given a data table along with a very detailed title, which gives you all the information you need, essentially. Or you might be just given a question without a data table. But in any case, there'll be enough information in there for you to follow your predicting redox reaction rules. So, first thing I'm probably going to do, if I see a data table is filled in, we can do our math. 11.6 mils. Okay, so I have a bunch of volumes, as you may recall, with titration. You don't use all of these volumes, you end up taking an average. And if you have 4 trials, solid chance that the first one is going to be too far out. Remember, we're only interested in the trials that are close to each other, i.e. within 0.1 or 0.2 mils. So I would take the average volume of trials 2 to 4, which will work out to be 11.0 mils. So that gives us a extra bit of information. I've got concentration of permanganate, I've got a volume of permanganate, and then I have a volume of the iron 2 solution that I'm titrating into. Okay, so first let's get our reaction just like we did before. So you'll see here I've got potassium permanganate and acidic iron 2. So the potassium permanganate would dissociate into potassium ions and permanganate. Remember, the permanganate does not break up any further as is a polyatomic ion. It says it's an acidic solution, which means it has H+. If it was basic, I would be incorporating hydroxide into there. Then I have iron 2. One of those metal ions, it's on both sides, and most times when you see redox stoich, you're going to have a metal ion as your SRA. It's a pretty good giveaway. Okay, so those are all my entities. Now, again, sometimes you want to save yourself some time. Look at the title. We now have permanganate reacting with iron 2. Well, chances are those should be my reacting entities, i.e. my SOA and my SRA. You'll see permanganate a lot, sometimes dichromate, because they change colors real nice, okay, especially when you have acid around, making them a stronger oxidizing agent. So list our entities right here, and I guess determine our SOA and our SRA. HMNO4 is our SOA, iron 2 ends up being our SRA. Now sometimes you guys will ask, well, which iron 2 do I use? It's on both sides. Well, let's take a look at our redox table again. So we have iron 2 down here as an oxidizing agent. Here we have it as a reducing agent. Well, it's an OA, yes, okay, as indicated down here, but it's our strongest RA, so this one I don't care about. Okay, this doesn't matter, that's an OA. I want to use it as an RA, so this is the half reaction I would use, the iron 2 turning into iron 3. Okay, so write out my oxidizing agent half reaction exactly as it is. Write out my SRA oxidation half reaction, the opposite. Okay, just reverse the reaction. And then I look at my electrons. I have a 1 electron loss. I have a 5 electron gain. So what do I got to do? All right, multiply the iron by 5, factor of 5, in order to balance those electrons out. Okay? And then I can get my net reaction from there. So now I can do my stoichiometry. From the data table, I had average volume of 11.0 mils, then I can start doing my math. Okay, so concentration of iron 2 is what I'm looking for. So I want some form of moles per liter. Start by determining my moles of my known. Well, what's my known? Permanganate, I can find moles for. Iron 2 is what I'm looking for. So MnO4 is my known. Find the moles using my volume, given volume and concentration. Many of you would be inclined to change the units into something, and feel free. However, the more often you change units, do any sort of conversions, the more likely you're going to screw up. Okay, so I always recommend don't change any units unless you absolutely have to, and usually you can do that at the end if need be. So I've now found the moles of my known. Next step, find the moles of my unknown. As always, use your mole ratio. Unknown coefficient over known. 5 moles of iron 2 for every 1 mole of MnO4. Moles of MnO4 will now cancel out. And right now I have millimoles of iron 2. It's kind of weird, but that's okay. Now I'm trying to find concentration, which means I need to divide my moles of iron 2 by the volume of iron 2, which is 10 mils. Okay, so then I work through that, and I look for my remaining units to help me out here. So what do I have? What's canceled out? So I've got those mils are gone with that milli. Okay, what's remaining? I have millimoles per liter of iron 2. Okay, we get ourselves a final number. 11 times 7.5 times 5 divided by 10. Notice I didn't do any conversions, so it can make my life a bit easier. So I end up with 41.3 millimoles per liter. Okay? That's fine. You guys like the standard units of moles per liter or something like that, go for it and change it, but I didn't make any changes. It's faster, less mistakes because I made less changes. Okay? And when you're thinking down the road for a diploma, you want to be as efficient as you possibly can.